Okay.
Okay. Do I start again?
Yep.
Welcome to another seminar in our Roadway Safety Institute series. We're going to have Professor Gary Davis talk to us today. But before I introduce him, just want to make sure that everybody out there in internet land knows that once they're on, they must click this button over here, right where the arrow's pointing, and that will allow them to sign in with their name, contact information, etc. And if you have any questions, please type them into the bubble that will appear. And Kylie, who's in the room here, will read them and ask Professor Davis any questions that you care to enter. Those of you who are taking the course for professional credit, there are forms available from Kylie in the back of the room. You can contact her by email as well. So without further ado, I'd like to introduce Professor Davis, who's been at the University of Minnesota since 1989 in the Civil Engineering Department, which is now called the Civil, Environmental, and Geoengineering Department. I have to study that new title. But anyway, what's really unusual about Professor Davis is that his original training is in psychology. He did his bachelor's and master's in psychology, and I believe his master's was on look at the effect of suicide intervention centers in Spokane County in Washington. But anyway, he decided that that wasn't what he wanted to do, and so he went back and got his other degrees in civil engineering. He got his PhD with Professor Nancy Nihan at the University of Washington, Seattle, who used to be a University Transportation Center director there many, many years ago. I believe she's retired now. But anyway, Professor Davis is, I think, one of the preeminent experts in this country on crash and safety statistics, and is well recognized for his work on the statistics related to crashes and safety. He's going to be talking to us today on model criticism and validation in crash reconstruction. And his hobby actually is in historical astronomy, but I don't think they're connected with his presentation today. So without further ado, go ahead.
Thank you, Max. See if we can live up to that introduction here. Okay, this talk is going to cover a bit more ground than the title suggests here. And maybe a way to start making a connection is a couple of weeks ago, Professor Benekal from University of Illinois was talking about looking at both macro and micro levels of what happens in crash and safety-related events. And this is somewhat related to that. Again, that's something that interests me, going from the micro level, which is the individual crash event, to more macro levels, which is aggregate statistics, such as you see in the Highway Safety Manual, for instance. So to get going here, maybe a place to start, David Shinar, a world-recognized authority on human factors in road safety, identifies three kind of general areas for trying to investigate causation, in traffic safety. All right, and the first is what he calls this, see if I can get this arrow to move here. I guess not. All right, well, we'll just go down here. Okay, the first one he calls theory-based clinical case analysis. And, oh, there it is.
Just put one finger.
Pushing hard enough here. Thanks, Max. All right, so we'll get up to here. Okay. Essentially, this is looking at individual crash events, and try to figure out what caused them. The exemplar study is the tri-level study done back in the 1970s. If you've ever seen some of those statistics that say that in crashes, in the neighborhood of 90%, have human factors, as a cause, and maybe 20% have road factors and 10% have vehicle factors, roughly those statistics. That probably dates back to this tri-level study here. The second is what Dr. Shinar calls statistical theory-free database analysis. That's essentially looking at crash records, okay, and then doing statistical analyses on these crash records to try to figure out what's going on. And this approach underlies the current edition of the Highway Safety Manual, for instance. And then the third, what Professor Shinar calls perspective in vehicle monitoring. It's kind of a new thing, okay? Naturalistic driving studies fall in this category where essentially you get a set of volunteers. They agree to have instrumentation placed in their vehicles while they do their normal driving for some period of time, and it collects information on what happens here. It's still kind of an open question. What's the best way, okay, to work with that kind of data, for instance? What I'm interested in is talk about today is the connection between the first two, okay, this theory-based clinical approach and then statistical approaches. So let's look at an example, okay, of a clinical case analysis. All right, this is an after accident scene diagram, okay, taken from a study down in Adelaide, Australia, back in the 1980s, and what it represents is a collision between a car and a pedestrian. And so, among other things that can be located here is a skid mark and a skidding distance up to the another skid mark and a skidding distance up to the point where the vehicle stopped, and then the distance between the point of impact and where the poor pedestrian ended up lying, okay, and in the crash reconstruction that's called the throw distance. And so a reconstruction of this basically, okay, there we go. All right, the speed limit on this road 60 kilometers an hour. Based on the skidding distances, the estimate was the vehicle speed at the start was about 73 kilometers an hour. The estimated point at which, the estimated point, okay, at which the driver noticed the pedestrian curting into the road, okay, was about 55.6 meters. And if the vehicle had been going at 60 kilometers an hour instead of what it was going, the estimated stopping distance is about 45 meters. All right, so the claim here is that if the driver had been going at the speed limit, the crash would have been prevented, okay, because the vehicle would have stopped before it got to the collision point. We call this counterfactual prediction. All right, we're basically making a prediction about what would have occurred had things been different than what they really are. And this sort of counterfactual prediction is kind of what lies at the basis, okay, of most clinical approaches, okay, to trying to look at crash. Kind of a quick summary of a comparison of some statistical methods and some clinical methods. Late 1970s in Zurich, Switzerland, okay, they lowered the speed limit on 60 kilometer an hour roads to 50 kilometer an hour and found a roughly 25% reduction in pedestrian fatalities. That's a statistical estimate. The folks down at Adelaide, Australia, okay, coming out of their pedestrian study that we just took a look at, all right, reported that based using counterfactual prediction, all right, that a 10 kilometer an hour reduction with similar compliance, okay, would have resulted in about a 27% reduction, okay, in pedestrian fatalities. Okay, so kind of roughly similar, okay, statistical and clinical estimates, okay, of this effect here. The Adelaide folks, okay, then extended their methodology and looked not only at pedestrian crashes, but a bunch of angle and turning crashes, runoff road crashes. And there they made some estimates, again, based on counterfactual prediction, okay, that a 5 kilometer an hour reduction in speeds would reduce about 15% of these, and a 10 kilometer an hour about 41.5%. And then kind of looking down at the bottom, okay, Ezra Hauer and Jim Bonison developed some regression models that relate speed to crash frequency. And based on their regression models, okay, they found reductions of 5 and 10 kilometers an hour, okay, that are not all that different, okay, from what the folks down in Adelaide found, all right, with their clinical study here. So this intrigues me. These correspondences could very well be coincidences, but I think it's worth at least taking a look, okay, to see if these two different procedures are successfully getting at some underlying feature, okay, of these crash processes that we can, you know, take a look at here. Okay, so anyway, what I'm going to do in here, okay, is take a look at two questions. One, under what conditions, okay, does the statistical and clinical approaches lead to similar results? And then second, the answer to one is going to require some assumptions. And then I want to take a look at some methods for checking and validating, okay, these assumptions, okay, in crash reconstructions. So a place to start, okay, a simulation experiment we did a while ago. We're simulating the effect of traffic conditions and stuff on heedless pedestrians on a residential street. So the basic model is a pedestrian runs into the road without looking. If there happens to be a vehicle nearby, okay, the driver attempts to brake to a stop without hitting the pedestrian. And our initial conditions, okay, the traffic flow on the street, 138 vehicles an hour with a mean speed of 30 miles an hour. And then we want to simulate the effect of two countermeasures. One is an automated collision avoidance system. And the way this ACAS works is that there's some sort of maybe radar-based detection, okay, that tells if a pedestrian is coming. If a pedestrian is coming, after a 1/2 second reaction, okay, then the ACAS automatically brakes the vehicle at 0.8 Gs. And then the other countermeasure is speed humps. And the effect of the speed humps is to both reduce the flow down to 88 vehicles an hour and the mean speed down to 25 miles an hour. All right, and the speed hump effect is taken from a report we pulled off of the Local Road Research Board's website, okay, for something that was actually reported, all right, for a speed hump project. All right, well, we can simulate, okay, what are called crash modification factors. And the simulated crash modification factor for the ACAS comes out to be about 0.38, and for the speed humps about 0.64. And then we can go simulate what counterfactual prediction, where if we looked at just at crashes and did counterfactual prediction on them, what would they claim, okay, are the modification factors? And with the ACAS, again, we get 0.38, but with the speed humps, we get 0.33. And the interesting question is, why this difference? And hopefully I'll be able to explain that, okay, in a few slides. So, starting point. All right, Judea Pearl, professor of computer science down at UCLA, okay, has been working for years on, I guess, what you might call the basic problem, is how would I program a robot to interact with its environment and learn the causal structure of that environment? And so to make some progress on that, it's required coming up with a formal treatment, okay, of what we mean by causal structure here. And so what's illustrated here is a graphical model. And the inputs and the outputs of the model are kind of as such. U stands for background factors. X stands for whether or not the countermeasure is there. And then the arrows pointing into Z say that this variable Z, okay, depends both on the background factors and whether the countermeasure is in effect. And then Y tells us whether there's a crash there or not. And some stuff you can say about that. Okay, first of all, if we put a probability distribution on the background factors, we get a probabilistic causal model, and we can start talking about probabilities of events. The other thing to notice is that the presence or absence of the countermeasure and whether a crash occurs or not partitions the background factors into 4 sets. And the first, what we call U00, those are background conditions where a crash never occurs. Okay, whether the countermeasure is there or not, we don't get a crash. U11 down at the bottom is background factors where crashes always occur. They occur without the countermeasure, and they would still occur even if the countermeasure was there. Okay, U10, those are background conditions where a crash occurs without the countermeasure, but it does occur with it. And then U01 is the other. Okay, a crash wouldn't occur without the countermeasure, but a crash occurs with it here. So we can divide the set of possibilities, okay, up into these 4 subsets, okay, in this case here. And essentially what I've kind of illustrated here is an example of that, okay, going back to our pedestrian crash. Again, the background conditions are the initial distance, the speed of the vehicle, the driver's reaction time, and his braking rate. And then this Z kind of tells us how we think the countermeasure is going to act. And if the countermeasure is not in place, then the driver continues or selects whatever speed he normally would have taken. Whereas the countermeasure is in place, then the driver reduces his or her speed by 10 kilometers an hour. Okay, a real simple model here. And then the bottom, this outcome basically says we get a crash if the initial distance exceeds or is less than the stopping distance. Okay, otherwise if the driver can stop before he gets to the collision point, the crash doesn't occur. And then what's in the little graph is a partition. Okay, in the upper left-hand corner is those events, okay, where a crash never occurs, combinations of speeds and distances where a crash doesn't occur even in the initial situation. Bottom right hand, okay, is events where a crash occurs, whether the countermeasure is there or not. And then that band in the middle, okay, is preventable crashes. And then those little X's that are in there, those are speed estimates from a set of reconstructed crashes that were done down in Adelaide. And so I guess what you might see, for instance, is at least the crashes investigated here in that Adelaide study all fall in that preventable region. And so if you were doing counterfactual prediction, okay, what you would say is that basically 100% of these crashes are preventable, okay, if we had this 10 kilometer an hour speed reduction, for instance. So, all right, this just kind of restates how counterfactual prediction works. We investigate and reconstruct a crash to estimate the conditions, okay, that led to that crash. We simulate how we think the countermeasure is going to affect those conditions, and then we predict, okay, whether those changed conditions are sufficient, okay, to prevent the crash. And essentially what's being estimated here, okay, is a quantity that Judea-Pearl calls probability of necessity. All right, and you look at that little graph down there, and again I've lost my arrow and getting out of control here. The little line down at the very bottom, okay, it's a conditional probability. The event we're conditioning on is y equals 1 means a crash occurred, x equals 0 means there was no countermeasure there, and then the conditioned event, y sub x equals 1, means if the countermeasure had been present, the crash would not have occurred. So we're looking at, of the set of events, okay, where the countermeasure is not there and crashes occur, what's the relative probability of the subset of preventable crashes? That's what counterfactual prediction, okay, attempts to estimate. All right, so back to the relationship between statistical and clinical studies here. Imagine we're going to do an experiment to estimate a crash modification factor. So we go out and we get a random sample of n events, okay, where these are like potential crashes, n potential crash events where the countermeasure is absent, and we count the number of crashes in that subset. And then we get a sample of n events where the countermeasure is present, and we count the number of crashes in that event. All right, well, the Highway Safety Manual defines the counter or the crash modification factor as the expected crash frequency with the countermeasure divided by the expected frequency without. And so for this little study here, what that produces is the CMF is just a ratio of these probabilities assigned to that partition of basic events. In the numerator is the probability associated with events where crashes occur with the countermeasure, and in the denominator, the probability of events, okay, associated with where crashes occur, all right, without, okay, the countermeasure. Now, when we look at probability of necessity, okay, which is what we get from the clinical studies, when we estimate probability of necessity from the clinical study, what we get is something that's not quite the same as the crash modification factor. We get essentially the probability of preventable crashes divided by the probability of crashes without the countermeasure here. All right, so there's not an equivalence to these things. All right, what we can get from a clinical study is basically a lower bound of the crash modification factor, okay, but not the crash modification factor itself. Now, if the countermeasure is what they call monotonic, which means it doesn't cause crashes, so that that set 0, 1, okay, is empty, all right, then probability of necessity, what we can get from a clinical study, all right, will equal, okay, the crash modification factor. So having hammered out that, okay, one of the things we next took a look at was imagine I've got a sample of reconstructed crashes, and I go through and I estimate, okay, whether with the countermeasure present, whether the crash would have not occurred or not. I get this frequency. And then the question is, what happens to that frequency? What does it converge to as the sample size gets large? And you make some assumptions, okay? You make the assumption that, first of all, we understand the causal structure of these events. We assume that for the time being that we have perfect reconstruction in the sense that we estimate accurately, okay, what the input conditions for the crash are. And then we also assume that we have consistent sampling, okay, in the sense that we're getting a representative sample, okay, of the sorts of events here. All right, well, it's not a profound theorem. All the heavy lifting is done with the assumptions, but it essentially says that these three assumptions mean that this consistent sampling property of our sampling gets inherited by our method for estimating probability and necessity, okay, that also would converge if we just had big enough sample sizes. So when I go back to my little simulation study, again, okay, the crash modification factor as simulated, 0.38 for the ACAS, 0.64 for the speed humps. And then from my counterfactual prediction, okay, I get some different numbers. First of all, the correspondence for the ACAS and the ACAS correspondence between the simulated and then what we would get from a clinical study, all right, is due to the fact that the ACAS is a monotonic intervention, okay, the way we simulate it here, whereas the speed humps are not necessarily monotonic, okay. They're basically the way that we modeled the change in the traffic flow. There were certain events that would not have been crashes under the first condition, all right, that turned out to be crashes under the second, okay. So the monotonicity property explains it. In addition, doing this counterfactual prediction for road-based interventions where we essentially affect the traffic flow conditions on the road is problematic to say the least. Because we have a crash, all right, we can go back and say, all right, the driver was traveling at a certain speed and was probably at a certain position when the pedestrian ran into the road. But the question is, okay, under the countermeasure, what would that speed have been and where would that position have been? All right, it's harder to answer. Okay, if we're modeling a reduction of speed by, say, 10 kilometers an hour, then traffic flow theory tells us, okay, that if the flow stays the same, all right, then the distribution of distances has to change. On the other hand, if we want to keep the distribution of distances the same, then the flow has to change. So we run into trouble, okay, doing counterfactual prediction, okay, with interventions that affect traffic flow conditions. And one of the things we looked at was what we call a non-parametric approach, okay, that dodges around these issues. Okay, I'm not going to talk about it today, but let's just say it's not hopeless, okay, for those sorts of interventions as well. So what I want to do next, okay, so this connection between statistical and clinical approaches, okay, we've at least made some contact there, okay, and indicated at least some conditions under which a clinical investigation could lead to a estimate of a countermeasure. And it looks like it's more promising for vehicle-based initiatives, okay, than it is for roadway-based initiatives, if the present state of knowledge here. All right, what I want to look at next is these consistency assumptions that we had to make. Okay, crash reconstruction is not an easy task. We made our mathematical task very easy by making some fairly strict assumptions. Okay, so I want to look at the realism of those assumptions here. All right, causal knowledge, perfect reconstruction, and consistent sampling. All right, it's possible to relax perfect reconstruction and do an uncertainty-based reconstruction. I'll talk a little bit about how that's done. And then for this consistent sampling, what we'd like to do, all right, is check and see, okay, that our reconstruction method is producing reliable results, okay, and then so I'll talk a little bit about validation, okay, and model checking in crash reconstruction. So again, I go back to our little example here, okay, this fatal pedestrian crash that happened down in Adelaide, okay, back in 1989. All right, and here's our basic results from that. And if you take a closer look at that, okay, in terms of like facts, the fact we have available, all right, is that the skidding distance was 23.5 meters, okay, more or less. Okay, we can take that as a fact. All right, the Reconstructionist's opinion is that the speed is related to this skidding distance, okay, by this expression here. That depends on both a drag factor, okay, friction term of 0.72, and an assumption that about 80% of the vehicle's kinetic energy, okay, is still available when the skid mark starts. That's an opinion, an expert opinion, but an opinion. The selection of values, okay, for the friction coefficient and the fraction of kinetic energy is an opinion. Okay, again, an expert opinion, not unreasonable, but an opinion. And so the output from that, okay, that estimate of 73 kilometers an hour, well, that's an opinion as well. Okay, as Stan Baker said a long time ago, all right, facts plus opinions equals opinions. So that number is an opinion. Okay, the question is, how do we do some stuff, okay, to make sure, or at least convince ourselves that that opinion is got some connection, okay, with empirical reality. Okay, that's kind of what I want to talk about next. Uncertainty in crash reconstruction. Ray and Matt Brock, okay, authors of one of the commonly used textbooks, okay, openly admit, okay, that anytime we make measurements, we've got uncertainty in a crash reconstruction problem. Dennis Lindley, statistician, recently passed away last March, I guess, okay, wrote what I found a very interesting paper back in 1991 on statistics and uncertainty in forensic science. And first of all, he argues, makes a good argument, in my opinion, for using probability as a logic for reasoning about uncertainty. And then he also identified two types of problems. Okay, one is kind of the classic forensic science problem. We're trying to identify a suspect, or we have a suspect and want to determine if that suspect's guilty. All right, the other is what Lindley called the case of a motorist charged with dangerous driving. Okay, here the criminal, quote unquote, is known, but what we don't know is whether there was a crime or not, okay, based on the background conditions. Okay, that's kind of the classic crash reconstruction problem here. And Professor Lindley said he didn't have much of an idea about how to do with this type 2 problem. All right, but we'll take a look at that, all right, in what follows here. So since Lindley's paper, the use of what are called Bayes networks have become not uncommon, okay, for attacking these type 1 forensic problems here. And this is just a illustration of a Bayes network put together for identifying or determining whether or not someone who is claimed to be the father of a child actually is the father of a child, okay, put together by Stefan Lorentzen, okay. There's a textbook on it, okay, that's come out recently here. And essentially what Bayes networks are, well, we've got all these variables represented as nodes. We have connections, okay, the connections represent probabilistic dependencies. And we want to be able to do stuff like, say, if I knew the value of one of these nodes farther down in the network, how does that change the probability assigned to nodes up in the network? Okay, in other words, how do we use evidence to change, okay, the plausibility, okay, of various hypotheses about how the evidence was generated? Essentially, that's what's being gotten at here. So go back to our crash reconstruction, pedestrian crashes again, and I've changed the notation a little bit, mainly because this is an old diagram and I didn't have time to draw a new one, okay, for the seminar here. But again, we got our pedestrian being hit by a car. X stands for the initial distance separating the driver and the pedestrian. S2 stands for the skidding distance after the point of impact. D stands for throw distance, and then down at the bottom line, it basically says that the distance, okay, from the initial position, okay, to where the vehicle comes to rest has 3 components. First is the distance traveled during the driver's reaction time, V times TP. The second is this braking transient. Okay, a little bit of time between when the driver gets his or her foot on the brake and it actually starts making skid marks, and then finally a skidding distance here. Okay, so here's kind of our simple collision model. And here's a Bayes network, okay, trying to represent that. So we have initial distance, reaction time, braking transient, initial speed, and braking drag factor as our inputs. Those in turn influence, for instance, the impact speed, V sub I. The impact speed in turn influences the second skidding distance and also the throw distance. And then the initial speed, the braking transient, and the drag factor also influence the full skid distance here. And so squares stand for things we can measure, and then the circles stand for things we're trying to infer. Okay, and so basically the issue here is, given a measurement of the throw distance and a measurement of that S2 skidding distance and the measurement of that S1 skidding distance, how do we refine our opinion about the values taken on, all right, by these input variables here? And that can be implemented. Okay, I won't go into a lot of details about how that is done. But essentially what this is a probabilistic reconstruction, okay, of that same vehicle pedestrian crash we've been looking at here. And so the red curve is basically the posterior probability, okay, that we would assign to the initial speed. And you can see it's centered somewhere around about 72, 73 kilometers an hour. And based on the evidence at hand, it was with high probability somewhere between, say, about 60 and 90 kilometers an hour. All right, so we start out with a very uninformative assumption about what that speed is, okay, basically between 0 and maybe 200 kilometers an hour. We look at our evidence, and the evidence then produces this posterior distribution. In the light of the evidence, okay, this is where the speed probably was. And then the blue line is essentially probabilistic counterfactual prediction. It's the probability that the crash would not have occurred as a function of a range of input speeds. So for instance, if the vehicle had been traveling at about 50 kilometers an hour, the probability of avoiding the crash is basically 1.0, all right, based on our estimate of the basic conditions. When we get up to 90 kilometers an hour, okay, the probability of the crash not occurring, okay, is essentially 0 here. And somewhere around 60 kilometers an hour, it's hard for me to say, but it looks like something like around 0.8, okay, is the probability the crash wouldn't have occurred. All right, so the upshot here is that assumption about perfect reconstruction can be relaxed, okay, to this probabilistic reconstruction, all right? And this is something we've been doing for a while here, okay, this sort of stuff. But again, opinions are inputs into this, okay? We use our expert opinion to come up with a range, for instance, of these braking rates, our expert opinion to come up with a possible range for driver reaction times. And so now I want to take a look at this idea of a well-calibrated opinion. All right. If you think about weather forecasters, okay, trying to forecast the weather, and say on a given day the chance of rain is 30%. Well, if we go look at all the days where the forecasted chance of rain was 30%, and if it turns out it actually rained on 30% of those days, we would call that forecaster well calibrated. On the other hand, if 50% of the days, okay, it was forecasted 30%, then the forecaster is not so well calibrated. All right, so we want to look at the calibration properties of our crash reconstruction. All right, and one way to look at it is, well, we have an estimated speed. We have a uncertainty range for that. All right, if that uncertainty range is associated with 95%, if my claim is 95% of the time I catch the true speed, and in fact, okay, I do catch, okay, that speed 95% of the time, then the reconstruction methodology is well calibrated. So what this graph shows, all right, is 15 vehicle pedestrian crash tests. Okay, now real pedestrians weren't used, okay, dummies were used. All right, but essentially what the authors of the book would do is get a dummy up there that kind of represents a pedestrian. All right, run into it with a car, okay, while the car's braking or not braking. You go out and measure skidding distances and throw distances. And so we take these measurements and do our Bayesian reconstruction on them. All right, now we actually know, for instance, what the impact speed was, okay, in these things here. All right, and so the bars are our 95% intervals, and then the X's are the actual speeds. And I guess what we can see is that in 13 out of the 15, okay, our 95% confidence interval catches, okay, the measured speed, suggesting that it's reasonably well calibrated. But in a couple of them, we don't do so well. And so what I want to look at here, all right, and I talk about model checking, is it possible to use the evidence to identify these miscalibrations, okay, and correct for them? So we introduced this idea of cross-validation. Okay, cross-validation, it's commonly used in statistics. We got a data set. What we do is we split the data set into two parts. And we use one part to estimate whatever model we're trying to estimate. Using the estimated model or model estimated parameters, we make predictions as to what the validation data set ought to look like, and then we do a comparison. All right, so we split the data set into two parts, okay, estimation subset and a validation subset. And it's generally recommended that's a good thing to do, okay, if you've got doubts about whether your statistical model really is describing what's going on out there. Some history, okay, for criticizing models in, I won't go through the whole history. What I will look at is this stuff by O'Hagan, okay, a paper he wrote back in 2003. HSSS stands for Highly Structured Stochastic Systems. And what he argued, for instance, a Bayes network, okay, is a highly structured stochastic system. All right, what we ought to be looking for is conflict, all right, in this Bayes network. And he didn't have a general method for looking at conflict, but suggested that would be a good idea. When you can find conflict in your Bayes network, that's evidence or suggests that your model is not as realistic as you'd like here. So how can we apply that to this case here? Well, what I have in this model here is we have the impact speed v sub I. All right, the impact speed affects both the throw distance, d, and also the second skidding distance, the skidding distance from the point of impact to where the vehicle stopped. All right, those are two separate measurements. And so what we can look for are those different measurements, the throw distance measurement and the S2 measurement, are they in conflict or not? If they are, okay, then that suggests we got a problem with our model. If they're not in conflict, then we can press on here. All right, so we call that an observational fork, all right, where we have a node of interest, like the impact speed, and then the arrows fork out to it, to two different measurements. Okay, when we have these observational forks, then we can use those measurements to play them off against each other to check to see if our method is working like we would hope it would work. All right, so I go through some detail on how the actual collision model, reconstruction model works, and I'll kind of go through that fairly quickly here. What I want to stop here, though, to take a look at is when we talk about vehicle-pedestrian collisions, they're generally identified several different types, or the way it occurs. Okay, the first is what they call the wrap, where the pedestrian rolls up onto the hood, okay, and then slides off. The second is what's called a forward projection, okay, where the pedestrian is just basically launched forward. All right, the third is what they call fender vault, okay, the pedestrian rolls onto the hood but now slides off to the side. And what's different between a fender vault and a wrap is that in a wrap, the pedestrian and the vehicle achieve a common speed somewhere along in there. All right, so what happens to the pedestrian can be used to estimate, okay, what the vehicle speed was. Whereas in a fender vault, that doesn't necessarily occur. Our reconstruction model assumes that we have wrap sequences. Okay, it was built on the assumption we have wrap sequences. Our throw model was calibrated to vehicle pedestrian crash tests using wraps here. So one way that we could have a problem, all right, is if this assumption of the collision type, okay, is not appropriate. Some stuff about how we fit the throw model. Okay, I'll kind of go through that real quick. Just an argument that it was not unreasonable. Essentially, we got 53 vehicle pedestrian dummy crash tests and fit a regression model, okay, to the darn things. All right, here's our basic assumptions, okay, for our reconstruction. The driver's reaction time, we assume that we're uncertain about that but it's bounded by 1/2 second and 2.5 seconds. The braking transient, okay, bounded by 0.1 and 0.5 seconds, okay, based on some measurements out of the literature here. The initial distance, anywhere between 0 and 200 meters, that's very uninformative. The initial speed, somewhere between 5 and 50 meters per second, again, very uninformative here. And then the braking drag factor, okay, the deceleration rate as a function of g, okay, we assume between 0.5 and 0.9. All right, those are a reasonable range of values for dry pavements where all the vehicles are locked and braking here. So that's another possible assumption problem. Okay, if all the wheels aren't braking, okay, then we could get a breakdown, okay, in our model here. So going back, okay, to my calibration test that I looked at a little bit earlier. All right, what I want to do is see if I can use, okay, cross-validation to detect, all right, these mismatches here. See, I can find these mismatches here because I happen to know what the actual impact speed was because it's a crash test. In a crash reconstruction, I wouldn't know that. So what I want to do is, can I use, okay, these cross-validation ideas to identify these situations, okay, where there's a mismatch, okay, and then maybe alert me to go take another look at my model here. So looking at this test 45-3, one of the things O'Hagan talks about is conflicts between your prior and your posterior here. And what we see here, all right, is that for our kind of down on the lower right-hand side, our braking drag factor, we assumed initially that it was uniform between 0.5 and 0.9. The posterior distribution for that is obviously not uniform. All right, that's a conflict, okay, between our prior and our posterior. The crash itself is not supposed to be informative, okay, about what the braking drag factor was. And when you look at that, what you look at is basically the reconstruction model is trying really hard to tell us that the braking drag factor might actually be below 0.5. Okay, all that probability piling up on the left-hand side is a clue, okay, that we've got the wrong assumption operating there. The other thing we can look for is conflict in posteriors, okay, and so here's a estimated impact speed based on throw distance and an estimated impact speed based on skidding distance, and we can see that they're centered over two different ranges, okay. The skidding distance estimates much higher speeds, all right, than the throw distance does, for instance. So here's stuff that we could get from a crash reconstruction, okay, and we're seeing conflict. And conflict means that we got to go back and revisit our assumptions here. What we want to look at next is a measure, okay, that kind of encapsulates what we just saw here. And Bayari and Berger, I think I pronounced that right, okay, a couple statisticians that have looked into this, okay, talk about what they call these p-values as measure of surprise, okay. In other words, am I surprised by my results? And essentially the way that works is I predict, all right, one of the measurements that I can make in my crash reconstruction, and I compare that to an actual measurement. And if that predicted measurement is out in the tail, okay, if the actual measurement is out in the tail of that distribution, okay, that's a measure of surprise. So for instance, we're going to look at throw distance. And what we'll do is we'll use the skidding marks to estimate the initial speed. Then we'll take that initial speed and predict what we think the throw distance ought to be, and then compare that to the measured throw distance. And if that measured value is unlikely, then there's a quantitative measure, okay, of conflict here. And so going back and looking at my 15 cases, all right, number 3, that 45-3, that's one of those where my 95% confidence interval failed to catch the true value. And my p-value there is 0.002. All right, what that says is that based on the skid marks and a braking drag factor of somewhere between 0.5 and 0.9, I would expect a throw distance that's actually quite a bit larger than what I actually observed. My observed throw distance is way in the left-hand tail. Only 0.002 of the probability, okay, of that predicted throw distance distribution is to the left, okay, of my measurement here. Another one crops up that we didn't catch the first time, okay, this in our comparison with the actual, and that's this 176-3, okay, where we get a p-value of 0.7. All right, which means that my measured throw distance is quite a bit larger than I would have predicted based on, okay, my skidding distances here. And then this one that also cropped up, okay, as problematic here, actually comes up with a fairly benign p-value, 0.43 here. So what we did is go back and take another look at these crashes, and I'll kind of go through this fairly quickly here. 45-3, okay, one of the things that was included, okay, with the book that had all this data were videos, okay, of these tests here, and these are some snapshots from the video here. Essentially, if you kind of look at it, okay, the pedestrian rolls up onto the hood and then appears to roll off to the side, okay, suggesting that we might have a fender vault, okay, instead of a wrap trajectory, for instance. Well, we studied the damage on the vehicle, okay, and there was contact damage actually on the windshield and on the vehicle's hood, okay, indicating that the pedestrian did make contact, okay, before rolling off. So that makes the fender vault a little less plausible. The other thing, okay, when you reread the crash, this test report, was that the way the driver of the test vehicle braked the vehicle was he didn't use the foot brake. Okay, what he did was yank up on the handbrake. All right, that locked the rear wheels but left the front wheels free to roll, okay, and braked that way here. And I guess my understanding is sometimes that's used in court cases, all right, where a skid mark estimates a very high speed, and then it might be argued that, well, no, the driver didn't use the foot brake, he just used the handbrake, okay, so the speed estimate is high. Anyway, that's what happened. And so, question, I guess, okay, was this partial braking, okay, the source, okay, of the problem here? So, an easy way to kind of capture braking is just imagine that now we're braking with only 2 wheels instead of 4. We cut our distribution, okay, in half, or essentially instead of an upper bound of 0.5, we used an upper bound of 0.25 for the braking drag factor. Instead of 0.9, we used 0.45. Rerun the simulation, and now instead of a p-value of 0.002, we get 0.22. All right, which indicates that it's probably a bit more plausible here. The impact speed now between 52 and 76 kilometers an hour, and the observed value 60. So now our 95% interval catches, okay, the test speed. And then we can also do what's called Bayesian model selection. Is we have these 2 different models. Okay, one, the 2-wheel braking on the top, the 4-wheel braking on the bottom. And we can compute, okay, the probability attached to both of those based on the evidence, okay, and the 2-wheel braking comes out to be much more plausible, okay, than the 1-wheel braking. All right, so for this example here, we were able to identify, all right, our probable source of the discrepancy in our model here, make an adjustment, and produce an accurate result, okay, using these ideas from cross-validation. All right, and so I've got some more examples, and I'm going to just kind of race right through them here because I want to talk just a couple minutes, all right, on this last event here. All right, this is an actual fatal pedestrian crash that occurred here in Minnesota, okay, and basically we got a 4-lane arterial with a very wide median dividing the traveled lanes. The posted speed limit was 50 miles an hour, And according to witnesses, apparently the pedestrian attempted to run across, okay, these two lanes here against the light. In other words, the drivers had the green light and the pedestrian, okay, had the red light. Or, yeah, the drivers had the green light and the pedestrian should have stayed. All right, tried to beat the vehicle and was not successful. All right. And so Minnesota State Patrol investigated it, okay, and some measurements, okay, total skidding distance, post-impact skidding distance, and throw distance, okay, were taken off their report here, and we went and reconstructed the crash. So again, looking for conflict, okay, between estimates. The impact speed from the skidding distance and the impact speed from the throw distance are roughly in accord. There's a lot more spread in the throw distance estimate, but they're centered at about the same places, okay, indicating that our braking model, assuming all four wheels were braking, okay, it was probably operating here. And then in the little bottom graph, here's our predicted throw distance, okay, using the vehicle, the skidding distance speed estimate to predict the throw, and then also the measured throw, which is just shy of 25 meters here. All right, and it's fallen there pretty much in the center of that distribution. So here it looks like we don't have much conflict. It looks like our model is reasonable. And so we go back and then estimate some stuff about the crash. The estimated impact speed, about 62 kilometers an hour. The initial speed, just shy of 88 kilometers an hour, with some ranges for those. The probability that the driver was going faster, okay, than 50 miles an hour comes out to be about 0.77, okay, so not egregiously high, but more likely than not. And then for the initial speed based on the skids only, I guess what you can see is when you combine the throw distance and the skids together to estimate the speed, the standard deviation goes down a little bit. The confidence interval shrinks a little bit, so we gain a little bit of precision, okay, from the throw distance and the skidding marks, okay, but not a lot, mainly because of the uncertainty, okay, with the throw distances here. So, conclusions. All right, counterfactual prediction is more likely to be useful in vehicle-based countermeasures. All right, for road-based countermeasures, we haven't talked about it, but we do have a non-parametric method that gets around some of these issues here. Both of these still require consistent, valid crash reconstruction. And when we want to look at doing validation checks for crash reconstruction, all right, when we have what we call these observational forks in our model, okay, we can use that to do some model checking and criticism. And then just for what it's worth, okay, it's fairly easy to implement this stuff, okay, using freeware off the internet called WinBugs. And with that, if you're interested in more details, okay, there's a couple papers that cover some of this stuff, and I'd be glad to take any questions.
If anyone in the room here has questions, I have a microphone. If anybody out in internet land has questions, they should be typing them into their bubble. Let me start.
All right.
Your discussion really focuses on having some historical evidence and using that historical evidence to develop these probabilistic models.
Mm-hmm.
But when you have people getting up and making these claims that if we had driverless cars, we would reduce all driver-related crashes, thereby eliminating crashes, that's based on conjecture and no evidence whatsoever. What do you say to that?
Well, it's based on a counterfactual prediction how these driverless cars are going to behave.
Well,
Whether they'll actually behave that way, I think that's an empirical question.
Which we have no way of knowing.
But we can start moving in that direction with data, for instance, from naturalistic driving studies. Okay, we might be able to start making some progress in that direction. All right, but yeah, it's still an open question what the actual safety effect will be, in my opinion anyway.
Certainly, who would have predicted people dying now because of airbag failures?
Or the types of
news
failures.
Of the last week and
Yeah.
the effect of faulty airbags and the gases in the airbags and how they basically exploded and killed several people. Any questions here?
You briefly mentioned court and how there's some of this evidence used in court, but to what extent is this statistical analysis able to be used in court for problems of speeding or whether someone was driving dangerously? Like just currently, how is that used?
Okay. I don't do court work. All right. I sometimes say if I can make it to my grave without ever being in a courtroom, I think that'd be just great. Okay. So I don't do the stuff. So I don't have any firsthand experience with that. There is interest in quantifying uncertainty in crash reconstruction. Okay. The best way to do that still seems to be an open question. All right. Every year or so, I present a paper like this at the SAE conference down there in Detroit. Okay, trying to at least argue, okay, that Bayesian methods are a plausible way to go about doing that, and we can handle some interesting cases. But the issue of probability and uncertainty in court cases, it's a big issue. I have a hard time summarizing it other than to say that you apparently have to be very careful about how you introduce that, okay, if you want to keep, okay, the jury, okay, on board.
Then, of course, there's the validity of the assumptions made in coming up with a model in the first place.
The devil is always in those details,
Right.
and there's a lot of room for sliding stuff in, okay, if there's not a real close attention to details. Okay, in our stuff, we try to be completely upfront. Everything I publish, I list the code that I use to do these, and so anybody else that wants to pull that out and do one, they can go ahead and do that. That's my view on it.
Well, it's certainly a day-to-day problem. I don't know how many of you paid attention just yesterday. An ice cream truck in L.A. killed an 8-year-old, and the question is, what was going on at the time? And you know, there are different witnesses, and everybody has a different impression of what was going on. There were some issues. Wasn't even in the last few weeks. Didn't some teenager hold on to a car while it was driving, and suddenly they released from the car, and they somehow ended up under the car. So again, nobody's there to witness what's going on, and so crash reconstruction comes in and tries to figure out what actually happened and who was at fault. So these are really tough questions, and again, lots of assumptions are made in the process of doing these accident reconstructions. So anyway, if there are no further questions, please join me in thanking Professor Davis for his talk, and if there are no further questions, thank you.
Okay. Thank you, Max.